Our planet Earth, a magnificent sphere of life and geological wonders, is also a place of constant change. Deep within its core, forces are at play that can unleash tremors capable of reshaping landscapes in an instant. Earthquakes, these sudden releases of energy from Earth's crust, remind us of the raw power that lies beneath our feet. While we cannot control these powerful forces, we can certainly prepare for their arrival. This is where the ingenuity of earthquake engineering comes into play. Through innovative design, advanced materials, and a deep understanding of seismic forces, engineers have made remarkable strides in mitigating the destructive potential of earthquakes. This is the story of how we are learning to live in harmony with a planet in perpetual motion, building structures that can weather the storms Earth throws our way. From the foundations to the rooftops, the future of construction lies in our ability to create resilient structures that stand strong against nature's fury. For centuries, builders have sought ways to make structures more resistant to earthquakes. Early civilizations often relied on trial and error, learning from past disasters to improve future designs. Over time, these empirical observations evolved into more formalized engineering principles. One of the most significant breakthroughs came with the development of reinforced concrete. This composite material, combining the compressive strength of concrete with the tensile strength of steel, revolutionized construction. Reinforced concrete allows buildings to flex and bend rather than crack and crumble when subjected to seismic forces. Another key concept is the use of shear walls and cross-bracing. These structural elements act like internal bones, providing lateral stability to buildings. They help to resist the sideways forces that earthquakes generate, preventing structures from swaying too far and collapsing. Base isolation is another effective technique for mitigating earthquake damage. Imagine a building resting on giant shock absorbers. That's essentially what base isolation does. By separating the building from the ground, this technique allows the structure to move independently of the Earth's movement during an earthquake, significantly reducing the impact on the building itself. The quest for earthquake-resistant materials goes beyond traditional concrete and steel. Researchers and engineers are constantly exploring new frontiers, seeking materials with even greater strength, flexibility, and resilience. One promising area of research is the use of shape memory alloys. These remarkable materials possess the unique ability to remember their original shape and return to it even after being deformed. Imagine a building that could literally bounce back from an earthquake. Shape memory alloys have the potential to make structures not only earthquake resistant but also self-healing, reducing the need for costly repairs after a seismic event. Another exciting development is the increasing use of recycled materials in earthquake-resistant construction. Recycled plastics, for example, are finding new life in building components, reducing both waste and the demand for virgin materials. This not only benefits the environment but also makes construction more sustainable and cost-effective. The fight against earthquakes isn't just about stronger materials. It's also about smarter engineering. Advanced technologies are being developed and deployed to outmaneuver seismic waves and minimize their impact on buildings. One such innovation is the tuned mass damper. Picture a giant pendulum placed at the top of a skyscraper. As the building sways during an earthquake, the pendulum swings in the opposite direction, counteracting the motion and reducing the building's overall movement. Tuned mass dampers act like giant shock absorbers, keeping buildings stable even in the face of powerful seismic forces. Even more futuristic is the concept of seismic cloaking. This technology aims to make buildings essentially invisible to earthquakes by redirecting seismic waves around them. While still in its early stages, seismic cloaking holds the potential to revolutionize earthquake protection, creating safe zones within even the most seismically active areas. Section 5: Early Warnings, a race against time. While designing and constructing earthquake-resistant buildings is crucial, providing people with enough time to take cover is equally important. This is where earthquake early warning, or EEW systems, come into play. EEW systems work by detecting the first seismic waves released by an earthquake. These waves, known as P waves, travel faster than the more destructive S waves that cause the majority of shaking. By detecting the P waves, EEW systems can provide seconds or even minutes of warning before the stronger shaking arrives. This precious time can be the difference between life and death. It allows people to take cover, automated systems to shut down critical infrastructure, and emergency responders to prepare for the aftermath. EEW systems are a testament to the power of technology to save lives and reduce the impact of natural disasters. Section 6. Mapping the risks, seismic zoning, and building codes. Building structures that can withstand earthquakes is only part of the equation. We also need to ensure that buildings are designed to resist the specific level of earthquake risk present in their location. This is where seismic zoning and building codes come in. Seismic zoning maps divide regions into areas of different earthquake risk levels based on historical seismicity, geological formations, and other factors. Building codes then specify the minimum design and construction standards required for buildings in each zone. These regulations are essential for ensuring that all new construction meets the necessary safety standards. They provide a framework for engineers and builders to follow, ensuring that buildings are designed to withstand the expected ground motions for their specific location. Section 7. Case studies, success stories in earthquake engineering. The true test of any engineering innovation lies in its real-world performance. Fortunately, there are numerous examples of earthquake-resistant buildings that have successfully withstood significant seismic events, showcasing the effectiveness of modern engineering principles. One such example is the Taipei 101 skyscraper in Taiwan. Completed in 2004, this iconic building was designed to withstand the region's frequent earthquakes. During a 2002 earthquake, while still under construction, the building's massive tuned mass damper proved its worth, significantly reducing swaying and preventing damage. Another notable case study is the performance of buildings in Japan during the 2011 Tohoku earthquake and tsunami. Despite the unprecedented scale of this disaster, many modern buildings designed to the latest seismic codes survived with minimal damage, demonstrating the life-saving potential of earthquake-resistant construction. Section 8. The future of earthquake resilience, a glimpse ahead. As our understanding of earthquakes continues to grow, so too does our ability to design and construct even more resilient structures. The future of earthquake engineering is bright, with exciting innovations on the horizon. One promising area of research is the development of self-healing materials that can repair themselves after being damaged, reducing the need for costly and time-consuming repairs. Imagine concrete that can heal its own cracks, or steel beams that can realign themselves after bending. These self-healing materials could significantly enhance the resilience of buildings and infrastructure. Another exciting frontier is the use of artificial intelligence in earthquake engineering. AI algorithms can analyze vast amounts of data, such as seismic activity, building designs, and material properties to identify patterns and predict potential weaknesses. This information can then be used to optimize building designs, improve construction methods, and develop more effective early warning systems. Section 9. Conclusion: a safer world, one building at a time. Earthquakes are a fact of life on our dynamic planet. However, the devastation they cause doesn't have to be. Through the ingenuity of earthquake engineering, we are learning to coexist with these powerful forces, creating a built environment that is safer and more resilient. From traditional techniques like reinforced concrete and base isolation, to cutting-edge technologies like tuned mass dampers and seismic cloaking, we continue to push the boundaries of what's possible. The future holds even greater promise, with self-healing materials, AI-powered design, and more advanced early warning systems on the horizon. Every new building, bridge, and piece of infrastructure designed with earthquake resilience in mind represents a step towards a safer future. By embracing innovation, investing in research, and implementing sound engineering principles, we can create a world where earthquakes no longer need to